Okay, welcome everybody. It's a great pleasure for me to introduce our next speaker, which is Oscar Randal-Williams for this session. Oscar received his PhD in 2009 in Oxford, and well, since 2013, he is having a position at the University of Cambridge. Presently professor. He has been awarded several prizes, Whitehead Prize, Philipp Lepper-Hulme Prize, Danny Heinemann Prize, Robert Wolfach Prize, and very recently the Clay Research Award for profound contributions to the understanding of high-dimensional manifolds and their diffeomorphism groups. And yeah, so the stage is ready for the talk, which will be on diffeomorphisms of disks. Please.
Thank you very much for the introduction. So today I'm going to talk about diffeomorphism groups of disks. So what I mean by that is the following. I want to look at the topological group of all diffeomorphisms of the unit disk, say of dimension D, and I mean diffeomorphisms which are the identity near the boundary. Okay, and if you don't like having manifolds with boundary, then you can equally well take diffeomorphisms of Euclidean space that are the identity outside of some unnamed big compact set, and I mean them as topological groups, so endowed with the usual C infinity topology. For me, it's very convenient to discuss manifolds with boundary like the disk and so on, but if you want to think about closed manifolds instead, then you can think of it in the following way. So the group of diffeomorphisms of the d-dimensional sphere splits as a space as the orthogonal group, dimension d+1, which acts on the sphere in an obvious way, and this diffeomorphism group of the disk. So from that point of view, the group of diffeomorphisms of the disk measures the difference between the full group of symmetries of the d-dimensional sphere and the sort of obvious symmetries that we're used to, the linear symmetries or the orthogonal symmetries. So from this point of view, it's quite interesting to know what this group is. And so here are some lower dimensional examples. So the group of diffeomorphisms of the one disk is contractible. You can prove that yourself by linear interpolation. For the two-dimensional disk, it was proved to be contractible by Smale. And for the three-dimensional disk, it was proved to be contractible by Hatcher in the 80s. And there's a new proof of that using Ricci flow through singularities due to Bamler and Kleiner that you can hear about at this Congress as well. But these days we know that in every other dimension, apart from 1, 2, and 3, this group is not contractible. I'll say a little bit about why later on. And if it's not contractible, then I would like to know what it is. It's not a point, okay, so it's not probably lots of other things as well, but what is it? And the way I want to discuss this is via the thing about the classifying space of this group. Okay, so algebraic topologists in the audience will immediately know what I mean by that. But if you're more geometrically minded and you want a more geometric model, then you can take the following one. You can look at the space of Riemannian metrics on the disk, which are standard outside of a compact set or near the boundary, modulo the group of diffeomorphisms. So that's some sort of modulo space of Riemannian metrics on the disk, and that's a model for the classifying space of the diffeomorphism group. This is very convenient because I want to remember not just the homotopy type of the diffeomorphism group as a space, I want to remember it as a group, and taking the classifying space is exactly how that gets encoded in homotopy theory. Everything I say today that is new is collaborations with two brilliant and energetic young mathematicians, Manuel Kranich and Alexander Coopers, but I'll say lots of other things that aren't new as well. But everything that's new is joint work with them separately. So I want to start by telling you 4 short stories about the diffeomorphism group of a disk. So these are 4 sort of classical or semi-classical things that were known. And the first one is to do with smoothing theory. So smoothing theory guarantees us the following kind of remarkable equation. It says as long as the dimension is not 4, there are 4 spaces of symmetries of the disk and of Euclidean space, and they're related by this kind of miraculous formula. The quotient of the group of homeomorphisms of the disk by the group of diffeomorphisms of the disk is the d-fold loop space of the quotient of the group of homeomorphisms of Euclidean space by the diffeomorphisms of Euclidean space. It's kind of a remarkable formula. And there's something like this is true for any manifold. You don't have to put in the disk, but I want to only think about it in the case of a disk. Because these 4 groups that show up in this formula, 2 of them turn out to be quite simple. The first is that the diffeomorphisms of Euclidean space. We can just linearize diffeomorphisms. We write down the following interpolation. Given any diffeomorphism, we can look at this 1-parameter family of diffeomorphisms. It starts, or maybe when t is 1, it's the original diffeomorphism, and as t tends to 0, it converges to the derivative of that diffeomorphism at the origin, which is a linear diffeomorphism. And this is a continuous family of diffeomorphisms. And so that contracts the whole infinite dimensional group of diffeomorphisms to the finite dimensional group of linear diffeomorphisms of Euclidean space. And you can then contract that a little further, if you like, to the orthogonal group by the Gram-Schmidt process. So that says that the group diff of Euclidean space is actually an infinite dimensional group, strictly speaking, but it's homotopy equivalent to a compact Lie group. And we've studied those in topology for about 80 years, and so we know a lot about them. But there's another trick you can do as well. The homeomorphisms of a disk, which fix the boundary, you can scale the other way. Don't scale outwards, scale inwards. So in other words, move the support of the homeomorphisms closer and closer to the origin. And if you work topologically, so with homeomorphisms and not with diffeomorphisms, then this process converges. It converges to the identity map, and that proves that the group of homeomorphisms, well, boundary of a disk is contractible. It's called the Alexander trick. And so that means that the left-hand side of this equation has the following form. It's some contractible space modulo the diffeomorphism group of a disk. Well, that's a model for the classifying space of the diffeomorphism group of a disk. And the other side is then the default loop space on the homeomorphisms modulo the orthogonal group. So that means, given that we understand the orthogonal group very well, and in algebraic topology we understand how to take loop spaces and so on, knowing about the group of diffeomorphisms of a disk is essentially the same as knowing about the group of homeomorphisms of Euclidean space. So this is another motivation for asking these or trying to understand this space at all, but it's also a tool we can use to somehow, some things that are more obvious from one point of view might be less obvious from another. That's the first story. The second story is how you study diffeomorphism groups of things in general. So classically, there's a mechanism for doing this, a 3-step program, where you first answer the homotopy theoretic analog of the question. You then promote that to a so-called block version of the question using surgery theory, and then you promote that to answer the actual question you had in mind using what's called pseudo-isotopy theory. And the first 2 steps are, in principle, you can get a complete answer for the first 2 steps, but the last step you can't get a complete answer even in principle. The last step is only valid in the so-called pseudo-isotopy stable range. And that's known to be about the dimension of the manifold over 3. That's a very deep theorem of Igusa from the 80s. So that means even in principle, this method cannot give you a complete answer, okay? But it can give you a complete answer in this range. And this was used by Farrell and Xiang a long time ago to calculate what you get for a disk. And here's what they discover. For an even dimensional disk, you get 0 in this range. And for an odd dimensional disk, the rational homotopy groups turn out to be a copy of the rational numbers in every degree divisible by 4. So 4, 8, 12, and so on. So this, I've written ... but this is only valid in this pseudo-isotopy stable range. So the 0, I suppose I don't have to explain. I mean, if a group is 0, it's 0 in one way. But the non-zero things, I should tell you what they are. And they arise by the relationship between pseudo-isotopy theory and algebraic K-theory of the integers. And they basically come down to Borel's calculation of the rationalized algebraic K-theory of the integers. The reason that even and odd stories look a little different is because there's a certain involution on the algebraic K-theory of the integers given by sending a projective module to its dual, and that splits this into eigenspaces. And it turns out the negative eigenspaces contribute to odd dimensional disks, and that's almost everything. And the positive eigenspaces contribute, well, in fact, they contribute nowhere, it turns out. So these things will show up later, and you might see that I've drawn these Qs in blue, and that's because I'll always draw things in blue when they're of this Borel/Farrell-Xiang nature as an aide-memoire. So the third story starts with an idea of Kontsevich that he presented at the European Congress in 1992, which suggests using what he calls configuration space integrals to produce cohomology classes on these spaces B diff of a disk with a small variation. You take framings into account in a certain way, but it's only a very mild change. And there's many configuration space integrals, and he explains how to organize them in terms of what's called a graph complex. So a chain complex built out of graphs whose differential is given by edge contractions of graphs. And this idea was taken up by Watanabe in the extremal degree where you only look at graphs that happen to be trivalent. That turns out to be an extreme part of these graph complexes, and he worked out exactly what you get in that situation. And a big combination of a lot of his work can be put together as follows. So if the dimension of the disk is even, or if the dimension is odd and the parameter R is at least 2, then there's a surjection from a certain homotopy group of B diff of a disk onto a certain vector space of trivalent graphs. Okay, and it's incredibly irritating to give you a precise definition, so I'll give you a non-precise definition. The Rth space in this sequence is spanned by trivalent graphs of Euler characteristic minus R with certain decorations which are not drawn and which I won't say. modulo a relation, this IHX relation as it's called. So that's a local relation among trivalent graphs, right? Those are all three little pictures of trivalent graphs. And whenever you see one, you're allowed to cut it out and glue in the other two. And also modulo certain signs, which I won't tell you, but they account for why there's two flavors of this space, AR plus and AR minus, is because there's two sign conventions that can show up. This definition is, when you make it precise, you can just put it on a computer and calculate the dimension of these vector spaces, and you see that the first few look like this. And the only point I want to make is that they're not all zero. Okay, and Watanabe's theorem gives us surjection onto these spaces, so that means these homotopy groups over here are not all zero as well. That is a uniform proof that all of these be diff of a disk starting in dimension 4 are not contractible, because they have some homotopy group that surjects onto something 0. You'll notice that when the dimension is 3 or less, the homotopy group in question is sort of degenerate, and this doesn't tell you anything. So this is a source of non-triviality, clearly unrelated to this Farrell-Xiang source. For example, for even dimensional disks, this gives something, whereas Farrell and Xiang said it was 0 in the pseudo-isotopy stable range. So this is a new phenomenon that must be going on somehow. The final of my 4 stories has got to do with work of Michael Weiss. So as I said, smoothing theory relates the group of diffeomorphisms of a disk to the group of homeomorphisms of Euclidean space. I normally call that top D. And using topological transversality, you can define rational Pontryagin classes, not just for vector bundles, but also for topological bundles, the kind of bundles that top D classifies. So they're only defined in rational cohomology. And with the usual definition of Pontryagin classes for vector bundles, then there's some well-known formulas that you deduce as soon as you define them. They're sort of immediate from the definition. You discover that the nth Pontryagin class is the square of an Euler class if you're doing 2n-dimensional vector bundles, and you realize that the Pontryagin classes above that are all 0. Now, once all these things are defined for topological bundles instead of vector bundles, then you can wonder whether these identities should hold there as well. And in a very remarkable theorem, Michael Weiss proved that they don't. And he proved something stronger. He proved that for many n and I, in a quantitative way that I won't give, there exist homotopy classes on this space B top 2n that pair non-trivially with the Pontryagin classes. So of course, if you've got a homotopy class that you pair non-trivially with, then you can't be 0. But also, if you've got a homotopy class that you pair non-trivially with, then you can't be a proper cup product of 2 classes. So it also rules out the first equation. So knowing that homotopy classes exist, detecting a cohomology class is much better than just knowing the cohomology class is non-zero. And using this translation between homeomorphism groups of Euclidean space and diffeomorphism groups of disks, you immediately deduce various homotopy groups of B diff of a disk is also non-trivial from this, just a translation. If you're keeping track of indices, you'll see that the indices are somewhat different to the indices in Watanabe's theorem, and this is because it's a different kind of phenomenon. So these are some new phenomena. I've written these Pontryagin Weiss classes in orange, and everything that will show up in orange will be in orange because it's going to be related somehow to the Pontryagin Weiss classes. So I want to try to explain a pattern that includes all of these phenomena. So what Alexander Coopers and I did was to look at the strategy of proof that Michael Weiss had used, and instead of trying to use it to show that certain classes were non-zero, we tried to use that strategy to just completely calculate the homotopy of B diff of an even dimensional disk to the extent that we were able to. I'll show you the result, and then I'll talk you through it in a way that will be more comprehensible than it first seems. So here's the result. So if you look at a dimension, it's an even dimensional disk of dimension at least 6. And then the statement says in homotopy degrees less than 2n-1, there's no homotopy rationally. That is consistent with what Farrell and Xiang found for even dimensional disks. And then in dimensions bigger than 2n-1, the homotopy groups would like to be a copy of the rational numbers every 4 degrees, starting at 2n-1. And that's true if you exclude certain homotopical degrees. And within, so these complicated formulas I've written here that I'll show you a picture on the next slide, and then they'll be much more comprehensible than the formulas are. And if I is not outside of those ranges of degrees, then we just don't know what you get. And these Qs, yes, they're in orange because they correspond to these Pontryagin Weiss classes. So this is very difficult to pass, but this is somehow the correct way to understand it. This is a picture of homotopy groups of even dimensional disks. The dimension of the disk is horizontal and the homotopy group is vertical. The dotted sort of line is the old pseudo-isotopy stable range. So below that is where we used to know things. And everything with a white background is now a complete calculation. Everything in the white shaded region, that's just the true answer. That's what the homotopy groups are there. And the things with a shaded background, they're not a complete answer. There could be more stuff there, but anything that I've drawn does exist at that position. And as I've said, everything in orange corresponds to these Pontryagin-Weiss classes. And I've also drawn as numbers the lower bounds for these homotopy groups that come from Watanabe's theorem. For some reason, for even dimensional disks, you only get a rather sparse amount of stuff from Watanabe's theorem in this range. So that's what it's saying. So this excluded bands of degrees correspond to these lines of increasing slope, alternating blue and orange. And inside those regions, we don't completely know what the homotopy is. It can't just be these Pontryagin-Weiss classes because, as you can see, Watanabe's classes line up exactly with the middle of these bands. And so there must be something new in there. And indeed, Watanabe's classes are an example of the something new. So in a different direction, Manuel Kranich and I tried to use somewhat different methods to calculate the same kind of thing for odd dimensional disks. Here we had in mind a slightly different question, and the method was different as well. And so the form of the theorem is slightly different. It just is a complete calculation in a certain range. And it says that in degrees, if we're doing a 2n plus 1 dimensional disk, then in degrees up to about 3n, the homotopy groups are given by the Borel/Farrell-Xiang classes that we knew. That's a copy of algebraic K-theory of the integers. And then a copy of Q every 4 degrees, these Pontryagin-Weiss classes, and that's it in this range. And if you go back and, which you can't do, I suppose, but if you go back and look at the formulas I gave for the Watanabe classes, you'll realize there was a Watanabe class in this range. There was one in degree 2n minus 2. It's the first one. It corresponds to the theta graph. That's a trivalent graph. And that turns out to be, that turns out to coincide with this first Pontryagin-Weiss class for non-obvious reasons, but it does. So here's a similar chart in this situation. There's a lot more going on. All the blue stuff is these Borel classes, which only exist in odd dimensions. All the orange stuff is Pontryagin-Weiss classes. Below the gray, in the white shaded region is a complete answer, and the gray shaded region is not a complete answer. It's just a lower bound on what there must be in that region. So as you can see, all these Watanabe classes are indicated as well. It turned out to be a lot more of them for odd dimensional disks. So there's some 9-dimensional vector space in the first column there and so on. So let me say a little bit about how we did this. As I said, it uses an idea that came up in Michael Weiss's proof of this theorem about topological Pontryagin classes. And to build up to that, let me just point out that many results in geometric topology are somehow relative. So smoothing theory tells you about the difference between diffeomorphism groups and homeomorphism groups. It doesn't tell you what either of them are, but it tells you about the difference in a clean way. Similarly, surgery theory tells you about the difference between homotopy equivalences and so-called block diffeomorphisms. But it doesn't tell you what either of them are, it just tells you about the difference somehow. And similarly, pseudo-isotopy theory is about the difference between block diffeomorphisms and true diffeomorphisms. And in Michael Weiss's proof, he came up with something that you can think of as a new kind of relativization statement of this kind. Let me talk you through it. So it's quite general, but this is a toy and useful example. Suppose you have a manifold whose boundary is a sphere. Say a D manifold whose boundary is a D-1 sphere, and let's partition that boundary into 2 disks. And I want to call one of those disks, I'll call it half the boundary, because it is somehow half of the boundary sphere. And then he shows that there's a fibration sequence involving the diffeomorphism group of the disk, the diffeomorphism group of the manifold, and the self-embeddings of the manifold that only have to fix half the boundary, not the whole boundary. So I've drawn here a picture of, in gray, perhaps, is the image of such a self-embedding. Okay, half the boundary is fixed by the identity, and the other half of the boundary, not only does it not have to be fixed, it doesn't even have to go to the boundary of the manifold. It can and is encouraged to go into the interior of the manifold. Okay, so this is a fibration sequence. It exists for any manifold M. It's not very difficult actually, but it's a brilliant idea to do it at all. And the idea is that, as always with fibration sequences in algebraic topology, the game is that if you know two things, you can try to get at the other one. Okay, and here the point is that the disk is always the disk, but the manifold you get to choose. Okay, so you can try to wisely choose a manifold M, calculate something about the middle and right-hand terms, and then deduce something about the disk. And it's up to you to choose what M you want to use. So for example, when D is an even number, then this is a good choice, it turns out. It's the two-n dimensional version of the genus G surface with one boundary. It's a manifold called WG1. I've drawn it in dimension 2, but of course it's not in dimension 2. It's some high dimensional manifold of this character. And then Weiss's fiber sequence in this situation takes the following form: B diff of an even dimensional disk, B diff of this manifold, WG1, and B of the self-embeddings of this manifold, WG1, relative to half the boundary. That's the shape it takes. So why is this any good, right? We were trying to understand diffeomorphisms of a disk, which is quite a simple manifold. And I've claimed that I've made progress by saying all you have to do is understand diffeomorphisms of a much more complicated manifold, and then you'll be fine, okay? But the surprise is that that's true. It's much easier to understand diffeomorphisms of more complicated manifolds when they're more complicated in this precise way, so they have higher genus. So that's a theorem in the case of surfaces due to Madsden and Weiss, and in the case of higher dimensional manifolds due to Søren Galatius and myself. And I won't write down the answer, but I'll just tell you that the cohomology of this middle space, B diff of these WG manifolds, especially in the limit as G goes to infinity, is just completely understood. It's just a formula for it. It's a polynomial ring on certain generators, and we know what the generators are, and we know what they mean, and we know everything about it. It's completely understood. So the cohomology of the middle term is done. Certainly, if you can take G to be whatever you want it to be. The other point is that this right-hand term, this B of embeddings of these manifolds, can be accessed by this thing called embedding calculus. So this is a method for studying spaces of embeddings. And it works in this situation when the dimension is at least 6. And it's worth explaining something about that because, of course, diffeomorphisms are an example of an embedding, a very degenerate example of an embedding. And so you can ask yourself, well, you know, why can't I just study diffeomorphisms using embedding calculus and be done with it? Why do I have to do all this trickery? And the point is that embedding calculus only works when you're studying embeddings of codimension at least 3. And when you embed a manifold into itself, it typically doesn't have codimension at least 3. But then that's also an objection to why I'm saying you can use it for the right-hand term, because I am embedding a manifold into itself there. And the subtlety comes down to this business about boundary conditions. It turns out you have to measure codimension in a very specific way. Codimension of an embedding of one manifold into another means the following thing. You take the actual geometric dimension of the target, and you subtract the homotopical dimension of the domain relative to any boundary that you want to fix. And the point is that these manifolds, I mean, they're geometrically 2n dimensional, fine. But if you only work relative to half the boundary, they're homotopically n dimensional, because it's homotopy equivalent to a wedge of n dimensional spheres relative to a point. And so for the purposes of embedding calculus, this kind of self-embeddings well half the boundary is actually a codimension n embeddings. And so if n is at least 3, then you're good to go. So that's the advantage that you have when you weaken this boundary condition in this way. So there you go, right? You can get at the middle space, you can get at the right-hand space, so you can get to the left-hand space. But unfortunately, there's 2 issues. One is that step 1, the middle space, the theorem is about cohomology of this space and is essentially about cohomology of this space. Whereas, step 2 is essentially a method to compute homotopy groups of embedding spaces. So there's some tension there. You have to decide, I mean, what you're going to do about that issue. I mean, you want to compute, at the end of the day, you want to compute homotopy of B diff of a disk. And the second issue is that it's all very well to say, well, there's a thing called embedding calculus that will just do that. I mean, that's like saying, well, there's a thing called spectral sequences, you know, you can calculate whatever you like. You just have to calculate some spectral sequence. I mean, it's not so, just because there's a tool doesn't mean that you can wield it. So the 2 papers I mentioned, the one with Sander Coopers and the one with Manuel Kranich, they deal with these 2 difficulties in sort of orthogonal ways, and that's why they're completely separate kind of papers, and that's why the results that they obtain are somehow different in spirit. Let me just talk through those briefly. So the work on even dimensional disks, which is somehow what this picture is showing with Alexander Cooper's, there we decide that indeed homotopy is best. And we decide that the solution to problem 1 is to actually compute the homotopy groups of the space in the middle, B diff of WG1. Now, this space is not a very pleasant space from the point of view of algebraic topology. It's not a so-called nilpotent space. It's not the kind of space that knowing about its cohomology will automatically tell you things about its homotopy groups, because it's very highly not simply connected. Its fundamental group is essentially the mapping class group of that manifold. It's something quite close to being an arithmetic group of a reductive group. And so it's completely not nilpotent at all. It's quite close to being either the integral symplectic group or the integral orthogonal group. So you can't expect a very close connection between the cohomology and the homotopy of that space. So what you have to do is essentially something like calculate the cohomology of the universal cover. It's not quite that. There's a certain covering space called the Torelli space, which is analogous to the Torelli subgroup of the mapping class group in low-dimensional topology, and you have to access the cohomology of that somehow. Now, that's a space that has an action of this big arithmetic group, this symplectic or orthogonal group, and so everything you do from now onwards has to be in the land of representations of that algebraic group. That's good, it turns out, because it controls what things can happen. But it's something that you have to do, and that's quite involved in its own right. We also, of course, have to calculate homotopy of the right-hand side. So embedding calculus gives you a tower that decomposes your space of self-embeddings into a load of fibrations. And the fibers are described in terms of certain section spaces over configuration spaces. So that's a mapping space. So there's a spectral sequence for that as well, that decomposes in terms of cohomology of configuration spaces with coefficients in homotopy groups of configuration spaces. And you can calculate cohomology of configuration spaces by a spectral sequence that starts with the cohomology of the manifold. So there's 3 chain spectral sequences that you have to evaluate there. By something like a miracle, the first 2 we can completely evaluate and completely resolve all extensions. And the third one, the embedding calculus tower, we can't completely evaluate. We can estimate a little bit where things are and where things aren't. And that's what leads to this band pattern. The bands are exactly where we get stuck in the embedding calculus tower. And so we don't know how to resolve it. And so we just write a question mark in the theorem. And that's what we do there. The result for odd dimensional disks with Manuel Kranich is similar in spirit. We use a similar fiber sequence. We do it for odd dimensional manifolds. We use certain manifolds called VG1. They're like analogs of handle bodies of surfaces instead of surfaces. But apart from that, the strategy is very similar. The left-hand term is something about B diff of an odd dimensional disk. It's in fact so-called concordances of an even dimensional disk, but that's quite similar. And we try to run this program. There we decide that cohomology is quite good instead. So we leave the middle term as it is. In fact, we do a little bit of decorations to the middle term. We put framings on things, and that makes the middle term have trivial cohomology. So it's completely neglectable. But then the right-hand term is B of embedding still. We have to deal with that. And we decide not to use embedding calculus. Instead, we use the fuel that embedding calculus runs on, which is called multiple disjunction for concordance embeddings. And we use that somehow with our bare hands instead of putting it in the vehicle. We just somehow use it. And that lets us calculate things about the cohomology of the embedding space in that case, but only in a range where this concordance disjunction business is good. And that's why there's an absolute upper bound on the theorem about odd dimensional disks. It was only up to 3n minus a constant. If you wanted to go up to 4n minus a constant, you'd have to do tertiary disjunction or something of that flavor. So those are the kind of methods involved. Now, I'd like to spend the last part of the talk giving you a proposal that would explain what we're seeing here. Okay, so these 2 theorems that I've mentioned, they're not so easy, they're quite difficult, but you can take the view that we're doing in those something like science. We've gone and done an experiment, and we've got these charts, and now we have to decide, what is explaining this behavior. And not like we did a, 200-page calculation, that's what came out, like a more conceptual explanation of what's going on. So to me, the first picture with bands in it suggests something like the following. The homotopy groups of B diff of a disk is a superposition of some kind of phenomena that happen on different kind of wavelengths or frequencies. That corresponds to the bands getting steeper and steeper. Okay, and the kinds of phenomena that occur seem to depend on the parity of D. Right, the even disks and the odd disks look completely different. There was all this Borel stuff in the odd case, and there was no Borel stuff in the even case. But within each parity, the Rth phenomenon seems to contribute to homotopy degrees around R times D. That corresponds to the line of, or the band of slope approximately R, let's say. And there's a mechanism in homotopy theory that would explain exactly this. It's also invented by Michael Weiss. It's called orthogonal calculus, and I'll spend a little time talking you through that. So it turns out that to employ this, it's better not to think about diffeomorphism groups of disks, but to think about homeomorphisms of Euclidean space. The theory is better adapted to that. Well, it's in fact only adapted to that. So I'll change perspective and talk about B homeo or B top of Euclidean space instead. But as I talked about in this smoothing theory discussion, the homotopy groups are basically given by shifting and doing a small amount of violence to the charts that I showed you. So they look very similar. The strategy is not to think about B top RD for one D at a time, but to do it for all D at a time. So the proposal is to consider B top RD as the values of the functor from the category of finite dimensional inner product spaces to spaces that sends a vector space V to B top V. So B of the homeomorphism group of the vector space V. And we should use the fact that, well, vector spaces have symmetries. And so we have a whole action of the orthogonal group of V on B top V. But also we can include one inner product space into another. Has a canonical complement because they're inner product spaces. And then we can take a homeomorphism of the one that we were given and extend it by the identity in the other direction. So these define a functor on the category of finite dimensional inner product spaces and isometric embeddings. And orthogonal calculus is exactly about this kind of functor. The game is to consider such functors from finite dimensional inner product spaces to spaces, pretend that they were functions, and develop a notion of Taylor expansion for them. That's the point of orthogonal calculus. So if we're going to do Taylor expansions, then we should have something like derivatives. It is, after all, some flavor of calculus. And the derivative is very easy. If I have a vector space V, there's a canonical isometric embedding into V plus R. I can apply my functor to it to get a map from f of V to f of V plus R, and then I can take the fiber. The fiber corresponds to the difference in homotopy theory between two spaces. And I call that f1 of V. That's like the first derivative of V. And as soon as you have derivatives, then you can talk about what it means to be polynomial of degree at most R. Right? You're polynomial of degree at most R if you're annihilated by taking R plus 1 derivatives. So we now know what it means for a functor to be polynomial. It means if you do this R plus 1 times, then you're 0. What's less obvious is that you can canonically approximate any functor by a polynomial one. But you can, let's just take that as a given. So any functor has a best approximation by a polynomial functor of degree at most R. Okay? And if you have a function in ordinary calculus and you compute its quadratic Taylor expansion, and then you compute the linear Taylor expansion of that, then that's of course just the linear Taylor expansion of what you started with. And that's similarly here. These Taylor functors fit into a tower. So the second one sits above the first one and the third one sits above that and so on. So they assemble into what's called the Taylor tower of the original functor. So far, this is all quite formal, but there's a very non-formal thing in this theory, which is what the homogeneous polynomial functors are. So the fiber of the map from TR of F to TR minus 1 of F can only have a very particular form. It looks a little bit complicated, so my apologies to the non-homotopy theorists who might be watching, but it's not so bad. The only possible thing a homogeneous functor can do is the following. You get to choose a spectrum in the sense of stable homotopy theory with an action of the orthogonal group OR. And then you take your vector space, you tensor it with little r copies of the real numbers, you one-point compactify it to get a big sphere. You remember the action of the rth orthogonal group on it, on the first r coordinates, and then you smash those things together over the group OR. So you take the sort of balanced product over the group OR. That gives you a spectrum, and then you take the associated infinite loop space. Okay, formulas with many symbols are easier, right? Because it means that it's a construction of many, it's a sequence of many constructions instead of one black box construction. So something like this, although it looks fearsome, is not so terrible. And these spectra with OR actions, theta f of r, these you should think of as being the derivatives. of the functor. Okay, the kind of mathematical object that the derivative is a spectrum with an action of the orthogonal group. So one can do this, or one can start doing this for this functor that sends a vector space to be top of that vector space. So what's the zeroth Taylor approximation? That's always given by the following formula. It's given by the stabilization of the functor. You add on a trivial vector space of dimension n, and then you let n go to infinity. So in this case, that's just B top. And the homotopy groups of B top are well known. They're one dimensional in every degree 0 mod 4, and they're drawn in orange because they exactly correspond to these Pontryagin-Weiss classes. That's what they mean. The first derivative is, so that was just a space, the zeroth Taylor approximation, just a space, B top. The first derivative is a slightly fancy mathematical object, right? It's a spectrum with an action of the group O1. And this was essentially, although it was before orthogonal calculus was invented, this was determined by Waldhausen in the 80s. It's the algebraic K-theory of the sphere spectrum. In order to state that, he had to invent algebraic K-theory of ring spectra first. But once you do that, then you can state it, and it's true. And this is somehow shown up in our discussion, because what showed up in our discussion was the algebraic K-theory of the integers. But our discussion was only rational. And you can't tell the sphere spectrum apart from the integers rationally. And so the things that were in blue, these Farrell-Siang classes, they indeed really correspond to the algebraic K-theory of the sphere spectrum, not of the integers. But from our rational eyes, we can't tell the difference. So Manuel Kranich and I took these charts that I showed you and the details that go behind proving them, not just the charts, and use them to determine what the second derivative is. Let me just say a word about that. So if we go back briefly to this formula for the derivatives, you see I'm starting with a vector space V of some dimension, and the rth derivative, the way it contributes is I take what's essentially the rth smash power of V, and I apply that, and I take that suspension of the derivative, and then I divide out by this OR action. That means at the level of homotopy groups of the spectrum, theta FR, will contribute in degrees approximately R times the dimension of the vector space, plus or minus some constant. That's the only way they can contribute. So if we look back at these charts, these lines of, or these bands of different slope exactly ought to correspond to these different derivatives of the of this functor BT in some conceptual way at least. And so we went back and did that, and we looked at the line of slope 2, and using that you can discover what the second derivative is. And it turned out to be this rather simple thing. Is you take the spectrum of maps from the circle to the -1 sphere. The circle has an action of O2, so that's the spectrum with an action of O2, and that is the spectrum with an action of O2. That's the second derivative, at least rationally. So that's the formula. Now, something worth thinking about with this formula is that in some sense, it seems a lot simpler than the zeroth and first ones. I mean, algebraic K-theory of the sphere spectrum is obviously quite complicated, but even just at some naive level, like let's look at its homotopy groups rationally, this mapping spectrum only has finitely many rational homotopy groups. That corresponds to the fact that the bands are bands. They have a finite width. They're not infinite wedges. And because of this band picture, it seems very reasonable to think that perhaps all the higher derivatives should only have finitely many homotopy groups. When you come to that, then you think, well, it feels like it ought to be a quite finitary thing to explain them to somebody. That if there's only finitely many going on, rational spectra are essentially very little information. It's essentially an algebraic thing to describe to somebody. So how could we go about describing them? So small detour. So the relation to configuration space integrals suggests the following strategy. It suggests that you might want to think about homeomorphisms of Euclidean space by thinking about its action on the configuration spaces of that Euclidean space. So the spaces of finite subsets of that Euclidean space. But you probably shouldn't think about them as an action on a sequence of spaces one at a time, and that's it. You should probably remember various things, like, for example, configurations of endpoints has an action of the nth symmetric group that commutes with the action of homeomorphisms. So you should probably remember that. And you should probably also remember that when I have a configuration of n points, two of them can come together and sort of collide. And then what I sort of see macroscopically is a configuration of n-1 points. And so I should probably remember how all my different configuration spaces of different cardinalities of points fit together in some way, not just thinking about them one at a time. And all this data can be packaged very neatly into a thing called the little d disk software. It exactly does what I said here. It remembers all the configuration spaces, all the symmetric group actions, and all the ways configurations can degenerate into smaller configurations. And it's an opwad, which is neat. And by what I've said, it seems reasonable if you make a good model for this little d disk opwad that there should be an action of the group of homeomorphisms of RD on it. And I claim that there is, and so that gives us a map from B top, or B of the homeomorphism group of RD, to B of the homotopy automorphisms of this opwad. So if you allow me to do a small amount of violence, if you allow me to rationalize this opwad, and then take its automorphisms, then the homotopy groups of this object have been completely computed by Frest, Turchin, and Willwacher in the last few years. And I could draw up a chart for you similar to my charts, but I won't. I'll just tell you what some features you would observe if you did do that. The first thing you would observe is that it has exactly this band pattern. The answer for D even and odd is completely different, but the answers for all even numbers look the same with rescalings of degrees, and the answers for all odd numbers look similar with all rescaling of degrees. So it has exactly the same kind of band phenomenon. The second thing you would notice is that the analog of the 0th Taylor approximation, so the phenomena that show up the same on the same way at all scales, is 0 in this case. Okay, in the case of B top, in the case of homeomorphisms, it was this homotopy of B top. It was these classes every 4 degrees, these Pontryagin-Weiss classes. The other thing you would discover is that the first derivative looks like negative cyclic homology. Whatever that is, that's some sort of more or less well-known attempt to approximate algebraic K-theory, but it does not succeed in approximating algebraic K-theory, but it has a map from algebraic K-theory. In the case of B top, we got algebraic K-theory of the integers, or maybe of the sphere spectrum. We can't really tell because we're only doing things rationally. And in this case, it seems that you don't get that, but you do get something more or less well-known, negative cyclic homology. And apart from that, then you see that the higher derivatives have this finite width property. They only have finitely many homotopy groups. Many things here are in inverted commas because I don't actually have an orthogonal functor. So it doesn't really make sense to talk about 0th and 1st and so on derivatives. All I mean is that when you look at the homotopy groups, it looks as it would look if these statements were true. Okay. Again, it's more science than mathematics somehow that we're doing at this point. So let's assume that we can define an orthogonal functor with these values. It sort of seems reasonable. If I give you an inner product space, you can take the unit disk in that inner product space, and then you can look at the opwad given by self-embeddings of that disk, not an abstract disk, this one. And it seems plausible that you can cook up an orthogonal functor structure on that, and that you can cook up a map of orthogonal functors from BT to BA, refining the one that I said on the last board. And it seems plausible to me that if you do this, then the higher derivatives of these two orthogonal functors, meaning 2 and higher, should be equivalent. And the calculation that I did with Manuel Kranich of the second derivative, you can compare that with a posited calculation of the second derivative of this orthogonal functor, and you would discover that indeed they are equivalent. So that's somehow evidence for this, this hypothesis. So the proposal I want to make is, could it be that there's a complete description rationally of the classifying space for the homeomorphism group of the D disk, or sorry, the homeomorphism group of D-dimensional Euclidean space, given as follows: you take this automorphisms of the little disks opwad and you correct them in the minimal way that fixes the things that we know, the ways we know that they don't match. And that exactly corresponds to, I mean, these things that I said about B top not being correct and K3 not being negative cyclic homology is exactly what the first orthogonal derivative of these two things measures. So you could try to correct them in that way and then ask whether that's rationally Cartesian. That would imply that all the higher derivatives are the same, but it's stronger than saying all the higher derivatives are the same. Saying all the higher derivatives are the same is saying this, but only when you take the sort of analytic approximation of these functors. So it's somehow saying that plus maybe convergence of the orthogonal calculus tower is maybe something like what I'm suggesting. So if this were true, I think it would be a kind of remarkable relationship between things that don't seem like they ought to be very closely connected. Homeomorphisms of Euclidean space, algebraic K theory and algebraic L theory showing up in the form of B top, graph complexes, somehow glued together along only along negative cyclic homology. So I don't know how to do any of these things, but I think it's an exciting time to be alive. Thank you.
Okay, thank you very much for Oscar for a beautiful lecture. Yes, so I would also thank the audience for listening and hereby close this session. Thanks again. Bye.